Hello, Matthews. In this video, I'm going to cover the extreme value theorem. So let's get started. Extreme value theorem tells us if we have a function f that is continuous on some sort of a closed interval, and in other words, it's allowed, is allowed to have a value of a and b and everything in between, then it has at least one max and at least one minimum value. Now, a couple notes about this. The extreme value theorem gives us a guarantee, but even if the conditions aren't met, we might still have extreme values. So we can't just rely on the theorem to guarantee max or mins, but if the conditions are met, we are guaranteed at least one max or min. Now, extreme values can occur at the interior points or at the end points, which is why we have a closed interval. Let's look at an example. So right here we have a graph. I want to see if the extreme value theorem applies, and if it does, we're going to look at some of the functions extrema. So if you look at this between -3 and 1, it is a continuous function. That is the key. It's a continuous function, yes, so I can apply the extreme value theorem. So I'm guaranteed at least one max and at least one min. Well, if you look over here, I have a minimum value, I have a minimum value, and up here I also have a max value. So those are all my extrema on that interval. Let's look at this one. Okay, so looking at this between -2 and 3, I can see, looking at the continuity, is this continuous? No, it is not continuous. It has a break in the graph. But even though it's not continuous, I can see that I do have maximum and minimum values. Okay, so over here I have a maximum value. Over here it looks like it's a minimum, but it's an open dot, so it doesn't actually include that point there. And over here we have a minimum. We're going to talk about what kind of a minimum that is later. And over here we also have another maximum. Again, we will talk about the types of max or mins that apply. But between -2 and 3, even though we can't apply the EVT, I can see that it still has max and min points. Okay, let's look at this one. For each function, determine if the EVT applies on the indicated interval. Okay, so if I look at g of x, again, I am looking for continuity. So this is an exponential function, and exponential functions are continuous everywhere. So that means that the EVT does apply for this. Okay, over here I have a rational function. Now let's look. Rational functions, I'm not allowed to divide by 0. So I know that x minus 2 can't be 0, which means x can't be 2. And since 2 falls in that interval there, the EVT does not apply on this interval. Okay, so now that we know when it applies, let's look at what we can figure out with it. So we can talk about critical values. Now, a critical value, first of all, is an x value. We say x equals c, c for critical value, and it has to be in the domain of f such that the first derivative of the function for that value c is 0, or the first derivative for that c critical value does not exist. Now, if x equal to c is a critical value, then we can put that together with the y value, c comma f of c. That is now called a critical point. Point because it has an x and a y. Now, critical points have the possibility, not guarantee, possibility of being a max or a min. So let's try and find the critical value of h of x. So h of x is a square root function. And first thing I know about square roots is that I cannot square root a negative number. So at minimum, it has to be greater than or equal to 0. Now this is a quadratic inequality. I always want to look at those graphically. So graphically, I can look at that picture. I know my x-intercepts are at -2 and 2. And I'm looking at where it's greater than 0. So that's on this side, and it's also on this side. So I know that I have an overall restriction that x has to be greater than or equal to 2, or it has to be less than or equal to -2. So basically, anything between -2 and 2 would not satisfy the original function. That restriction goes throughout the whole question. Now, let's find the first derivative. So x squared minus 4 to the 1/2. So my derivative, use power law, bring the 1/2 down, decrease my exponent by 1, and then chain rule, derivative of the inside. Okay, so half of 2x is just x, and then this negative exponent can be made positive by bringing it to the denominator, And since I started with roots, I'm going to end with roots in the denominator. Okay, so we said critical values are the value that make the first derivative equal to 0. So if you look at the numerator, that would just be x equaling 0. And we also said that critical values are the values that make this equal to does not exist. Okay, and so for this, when does that function not exist? Well, that function does not exist when x is greater than or equal to 2 or less than or equal to -2. So we have some potential critical values at 0 and at positive and -2. But remember I said that that overarching domain restriction applies to the whole question. It can never be 0 because that's not in the domain. So we don't even have to consider that. So our critical values for this are x values of positive or -2. Now, what we can do with those critical values is find our critical numbers, which are our local max or min points. Okay, so we can have local or absolute max or min points. Let's talk about local first. These can only occur at critical point on an open interval. So that's the in-between. Absolute max or min can occur at a critical point or at an end point. So if I have an end point, that therefore is a closed interval. So local max or min only in between the end points. Absolute max or min could be in between or the actual endpoints themselves. Let's look at some examples here. So for this graph, I just want to identify some local, absolute, max min points. Okay, so if I look down here, this looks like it's a minimum point, but it's not existing. It's an open dot. And this here continues for infinitely in the negative direction. So technically, I don't have a absolute minimum there. So we go to the top here. Now I see over here, I have a max, and it looks like it's the same as that. So I'm going to call this one here an absolute max and an absolute max. And then here I dip down, so I have a minimum, but since this graph here goes to negative infinity, it's not an absolute. It would be a local minimum right there. Okay, let's try another one. This graph here. So we have a closed interval. Let's look at maxes and mins. So over here, it's a closed interval that includes that point. This is the absolute maximum point. There is nothing more maximum than that. Now, I do have another maximum in this area, but it's local, which just means in that area. Okay, over here I have a minimum point, but this is the most minimum. So I'm going to put that as an absolute minimum, which means that in this area here, that would be a local minimum. Okay, so absolute, absolutely the highest or the lowest, local, high or low points in a particular interval. Okay, so to find the absolute max or min values, what we're going to do is we're going to, first of all, check our endpoints. Second of all, take the derivative and find the critical values to find that. And you're going to evaluate all of those numbers and see which one is the biggest y value, which one is the biggest or the smallest y value. So remember, absolute max or min values are y values. Okay, so let's end with this example on the next page. So I want to find the absolute max and min for these values on this interval. Okay, so very first thing I'm going to do is evaluate at 1. So I'm going to have 1 cubed minus 6 times 1 squared plus 8. So when at our endpoint of 1, I'm going to have 1 take away 6 plus 8. So that is going to be 3. Okay, now I'm going to do the same thing for my other endpoint of 6. So I'm going to look at the value of the function at 6. So 6 cubed minus 6 times 6 squared plus 8. Okay, so let's do 6 cubed first. That is 216. Take away 6 times 6 squared, which is also the same as 6 cubed, plus 8. So that is going to be 8. Okay, now let's find our derivative. So the derivative, f prime of x, is 3x squared minus 12x. Now, this is defined everywhere. It's a polynomial, so that means that that first derivative is not going to be undefined anywhere. So we just want to set it equal to 0. Before I do that, I will factor. So I'll take the 3x out, and I'm left with x minus 4. So here I'm going to have a critical value at 0. Here I'm going to have a critical value at 4. So I'm going to do the same thing, finding those values there. So f of 0 is going to be 0 cubed minus 6 times 0 squared plus 8. So that is 8. And then I will do the same thing for 4. Okay, so I'm going to do 4 cubed minus 6 times 4 squared plus 8. Okay, so if I do 4 cubed, that's 64. Take away 4 squared is 16, and 16 times 6 is 96 plus 8. So simplifying that, I have 64, take away 96 plus 8 is negative 24. So to find the absolute max and min, I look at my absolute highest point, which I can see is 8. Okay, a y value of 8. So I have an absolute max at 6 and 8 and 0 and 8. And then I have an absolute minimum value, the lowest value at negative 24. So that would be at 4 and negative 24. Okay, so talking about these absolute highest maxes and lowest mins reminds me of a little math joke I once upon a time heard about a teacher who asked the student to come up and write the largest number that they possibly could. So the little student there, we'll call him Mateo, went up to the board and wrote a ginormous 1, largest number he could. Thought that was great. So I hope that this video helped. If it did, please give it a thumbs up and hit subscribe so I can help more mathies just like you. Thanks for watching, and we'll see you for the next one.